Okay, in this video we're going to look at some examples involving the projection of one vector onto another. We're going to do 2 in 2D, one where theta is acute and another one where theta is obtuse, and then we'll do one in 3D. In 2D we can visualize a little bit better what's going on by graphing it, so I just wanted to show you what happens when theta is acute and obtuse in a version that you could really see, that can be made a little bit more concrete for you through graphing, through visualization. Okay, so I've got these two vectors, and first I want to compute the dot product. That's easy, you just multiply component by component. So take the x component and the x component, multiply those together, and then take the y component and the y component, and multiply those together. And so I get 9 plus 21, so the dot product is 30. Now remember what we said in the last video, if that dot product is positive, that means the angle between the two vectors is acute. Okay, it's good to know. I know it says to sketch last, but I think I'm going to sketch first. I want to go 9 units in the x direction, 7 units in the y direction. I'm going to try to make this as nice as possible, make all my tick marks evenly spaced. So I'm going to go 9 units in the x direction and 7 units in the y direction. And at the point 7, 9, I'm going to use another piece of paper as a straight edge. 7, 9 is right there approximately, that corner. So this is my vector u. And the vector v goes 1 unit in the x direction and 3 units in the y direction. So 1 in the x, 3 in the y. I think I want to use blue for the v. And that's the vector v. So I want one component of u that's parallel to v and another component of u that's perpendicular to v. Actually, I think I may have drawn my dot product through it. Maybe I didn't give myself quite enough space. Now the projection of u onto v is going to be on this line. It's the part of u that's parallel to v. And we're talking about the vector projection. So the part of u that's parallel to v is going to be on this line. And to find the part of u that's perpendicular to v, I think I'm just going to put my straight edge here and go out to that point. Just going to draw it. That's w. And this vector that starts here and ends there, that's the projection of u onto v. Okay, these guys meet at 90-degree angles, so that this plus this equals u. Okay. Alright, so now let's just use the formula to find the projection of u onto v and see if that agrees with our picture. Well, according to the formula, the projection of u onto v is the dot product of u with v divided by the length of v squared times the vector v. Okay, so I've got v here, and I already know the dot product. I calculated that earlier. That was 30. So I need to find the length of v and actually square it. So that's just going to be the sum of the components squared. Or you could take the length and then square it. That would work too. So we're going to have 1 squared plus 3 squared. So that's going to be 1 plus 9, which is 10. So it looks like the projection of u onto v is this dot product, which was 30. Calculated that earlier. Here it is. And then we're dividing by the length of v squared, which is 10. And then you just multiply the whole thing by v. So it looks like the projection of u onto v is just 3 times v. So it's 3 times the vector 1, 3. And that's the vector 3, 9, from what we know about scalar multiplication. Look at my picture. It's not perfect, but does it look like it's approximately at 3, 9? Well, not exactly. But maybe if I drew a better graph, that could be 9, and that down there could be 3, if I had done everything perfectly correctly. If I had graph paper, it would be perfect, right? As long as it's counting the right number of boxes. So my dot product was 30. And the projection of u onto v is 3, 9. And the question becomes, well, what is w? What do I have to add to this to get u back? Well, according to our formula, w is u minus the projection of u onto v. So I'm going to take u, which had components 9, 7, and I'm going to subtract the projection, which is a vector with components 3 and 9. When we subtract component by component. 9 minus 3 is 6. 7 minus 9 is negative 2. Does that look like what we've got here? I hope so. I know it's not to scale. That doesn't really look like 2 units, but we'll say that that was 2 units. It's not to scale. So according to this, we go down 2 units and 6 units to the right. So down 2 in the y direction and over 6 units in the x direction. So it's down 2 and over 6. And if this was lined up with 3 like it was supposed to be, that would work. And then we would end up at 9, 7. It's not a perfect picture, but you get the idea. If I take the projection and w and I add them together, I get 9, 7. And that's the u that we started with. And the projection of u onto v, that's just 3 times v. So I took v and I made it 3 times longer. And that was the projection of this vector onto this one. So you can be split up into these 2 pieces, this one and this one. They add together to get u. And this one is just the part of u that's parallel to v. Okay, so that is where theta is acute. Here's my theta. It's clearly acute. So let's do another example where theta is obtuse. So let's not do it on this paper. Okay, so let's do one where theta is obtuse. Here I've got u as the vector 6, 7, and v is the vector negative 1, negative 4. And we want the projection of u onto v again. So we're going to do the dot product, we're going to find the projection of u onto v, and then we're going to find w. Okay. And just to visualize what's going on, I'm going to draw myself a picture. I'm going to go 6 units in the x direction, 7 units in the y direction, and use a piece of paper to plot that point. It's the terminal point of my vector u. It's a vector with components 6 and 7. And I also want to draw the vector v. So this says go -1 unit in the x direction, and then down 4 units in the y. So I'm going to use blue for v, go over 1 and down 4, and that's v. So looking at my picture, it's clear that my angle, the smaller angle between the two vectors, is obtuse. And if I want the projection of u onto v, oops, I should have drawn an arrow here, v points that way. My projection of u onto v is actually going to point that way. So I'm going to draw a line, the line that contains the vector v. Just make it a dotted line. My projection of u onto v lies on this line. Okay. And the part of u that is perpendicular to v, or perpendicular to that line, or normal to that line, the component that is orthogonal to the projection, those all mean the same thing, 90 degrees. The part of u that goes that way is there, calling that w. And the part of u that goes in the same direction as v, that's the projection of u onto v. It's the part that meets w. Okay, so now I just want to find those two. Now I want to find the dot product. Okay, so first we'll do the dot product, easy breezy, multiply component by component. So I'll do 6 times -1 plus 7 times -4. So that's -6 minus 28, so -34. And then if I want, that's my first part. Now if I want to find the projection of u onto v, according to my formula, I can take the dot product of u and v, which I just found, divide that by the length of v squared, that's just a number, and multiply the whole thing by v. So first thing I'm going to do is find the length of v squared. That's the same as v dotted with v if you prefer. You're just going to take v, and you're going to take the components and square them and add them. Now, if I was finding the magnitude, I'd square them and add them and take the square root, and finding the magnitude squared. So I don't need the square root. I just have 1 plus 16, so that's 17. It's actually very convenient. Okay, so now I'm going to substitute those into the projection of u onto v. My dot product is -34, so that goes there. It's that part. And then the length of v squared is 17, so that goes there. I wrote 32, I meant 34. And then I'm taking that scalar and I'm multiplying it by v. Well, 34 divided by 17, we all know that's -2. We see that the projection and v go in opposite directions. So the projection is twice as long as v, but instead of going this way, it goes that way. To find the projection, I'm going to take -2 and I'm going to multiply it by v. Distribute component by component, like we always do with scalar multiplication. Does it look like that's 2, 8? Again, it doesn't quite look like 2, 8. And I need real graph paper. It's supposed to be 2. It's not to scale. But that's the idea. We go 2 units this way and 8 units that way. It's twice the vector v, and that gives us the projection of u onto v. Now w satisfies this equation, W plus the projection has to be U. Because by design, this is the part of U that's parallel to V. This is the part of U that's orthogonal to V. So when I add these two guys, I'm supposed to get V back, or excuse me, U back. So if I want to get W by itself, I just subtract the projection from both sides. So I've got the vector 6, 7, and I'm subtracting the vector 2, 8. We subtract component by component. 6 minus 2 is the x component, 7 minus 8 is the y component. So I get 4, negative 1. That's my W. Does that look like what we've got here? Maybe, maybe not. Again, it's because my graph isn't perfect. So 4, negative 1. That means we go down 1 unit in the x, or down 1 unit in the y direction. That's what the negative 1 means. And then we go to the right 4 units. And if that was supposed to be x equals 2, this is x equals 6. So this is 4, and that's negative 1. So yeah, if I take this vector and this vector and I add them together, I do get that one. Or you can add algebraically. Is 2 plus 4, well, 2 plus 4 is 6. Is that the x component of U? Well, yeah, the U is the vector 6, 7. If I take 8 and negative 1 and I add them together, do I get the y component? Yeah, sure. This is going to, if I add, I get 6, 7, and U is the vector 6, 7. So we know we did it right. So this is what we're doing, guys. Anytime you find a projection of one vector onto another, you're just finding the part of this vector that is parallel to this vector. If the angle is obtuse, the projection is in the opposite direction from V, or, like in our last problem, if the angle is acute, the projection is in the same direction as V. And then the part of U that's orthogonal to V, that's everything else. It's the part that you'd have to add to this guy to get U back. Okay, so that's just a visualization. We did it in 2D with obtuse and acute angles. In 3D, the formulas still hold. It's just a little bit less easy to see. We can't draw the pictures as easily. But we can do all the calculations in much the same way, just using our formulas. So let's do a 3D example. I've got U equals the vector with components 8, 2, 0, and V equals the vector with components 2, 1, negative 1. We're going to take their dot product. So multiply component by component, and then add. So I've got 16 plus 2 plus 0, so that's 18. And then if I want the projection of U onto V, I write my formula down. I need the dot product, which I just found, divided by the length of V squared. I'm going to take that and multiply by the vector V. Now the length of V squared just comes from taking the components and squaring them and adding them. I would square them, add them, and take the square root if I wanted the length. If I want the length squared, I don't need the square root. So now I've got 4 plus 1 plus 1. So the length of V squared, or the magnitude of V squared, is 6. So we can substitute those two pieces in. So we got a projection of U onto V. Well, that's just the dot product. So 18 divided by the length of V squared, which is 6, times the vector V. So I get 3 times the vector V, and then I just multiply. I'll write my vector V in, and I'm going to distribute that scalar. It's in the same direction as V, that's good, 3 times as long. And that's the projection of U onto V. So we found our dot product, we found our projection, and then to find W, remember we take U and we subtract the projection of U onto V. So I had this vector 8, 2, 0, and I'm going to subtract 6, 3, negative 3. Remember, you subtract component by component. Eight minus 6 is 2. 2 minus 3 is negative 1, and that's just going to be a positive 3. So that's W. Now, just to check our work, let's make sure that the projection in W add to give us the vector V, or excuse me, add to give us the vector U. This is the part of U that's parallel to V, and that's the part of U, or the component of U, that is orthogonal to V. So it's parallel and orthogonal, or parallel and perpendicular if you prefer. Okay, so I've got 6, 3, negative 3. If I add that to 2, negative 1, 3, let's do that. You have 6 plus 2, and 3 plus negative 1, and negative 3 plus 3. If we simplify, get 8, 2, 0. Is that U? Oh, it is. That's good. That's U. It checks out. So these are the parts of U, one that's parallel to V, which is 3 times V, and then there's the rest of U, that you add these two guys together and you get U back.